Hello everyone, and welcome back. Last time we started looking at some thermal properties of materials, and we're going to continue with that today, our last lecture for this course. Lecture 24, Thermal Physics Overview, Part 2. To begin with, what we're going to do is limit our view for this lecture to a particular kind of system. We're going to assume that we've got a system made up of a whole bunch of individual particles, typically a very, very large number, and I'll explain that in just a second. But we're going to assume that they don't interact with each other. So if there are any forces between them from one particle to another, we're going to ignore those. So we're not looking at a solid or a liquid. We're looking at basically a gas where the particles are far apart. We're going to assume that the particles have no internal structure. In other words, there's no way for these particles to have energy other than their kinetic energy of motion. So however these things are moving in random directions, essentially, they'll have some kinetic energy, but there'll be no potential energy because we're ignoring any forces between them. Another way of looking at this is we're going to assume that the size or the volume of the particles is basically negligible compared to the overall volume of the container. So we'll assume that we've got some container containing all of these particles. And then under these conditions, we call this an ideal gas. It's a gas because the particles are free to move wherever they want. They're not restricted to being close to each other like they are in a solid or a liquid. And with no internal structure, the only kinetic energy they have is their kinetic energy of motion. Okay? Basically, we can think of these maybe as individual atoms or something like that. Typically, when we have a sample of gas, we have a huge, huge number of particles. So we're going to introduce a few new quantities, so to speak. We're going to introduce a new mass unit and then a number that we will use in order to describe how many particles here we have. Okay, so give me 1 second. The mass unit that we'll use is a very, very small mass unit, and it's a better mass unit to use when we're talking about individual atoms, or maybe not necessarily better, but it's a little bit easier sometimes. The unit is called an atomic mass unit, and we'll shorten that to AMU. It's defined as 1/12 the mass of a carbon-12 atom. Carbon-12 is the most common isotope of carbon, and it's easily accessible, and so it was used for this definition. And you can think of this as carbon-12 has 12 nucleons, in other words, 6 protons, 6 neutrons. 1/12 the mass of a carbon-12 atom then corresponds roughly to about the mass of 1 nucleon and 1 electron together. It's equal to just about 1.6605 times 10 to the minus 27 kilograms. And because we've got so many atoms typically in an ordinary everyday sample of gas, we're going to use another number to help us describe how many of these things we have, how many atoms. And it is called a mole. It's also known as Avogadro's number, and it is just about 6.022 times 10 to the 23. And sometimes we'll write this as capital N sub capital A. So where did this number come from? We know where this mass came from. It came from the definition of atomic mass unit. The Avogadro's number is the number of AMU in 1 gram. So if you write this in grams, 1.6605 times 10 to the negative 24 grams, and invert that, you get Avogadro's number. So a mole is the number of atomic mass units in 1 gram. Okay, very good. Now let's use, in particular, we define this, but what we're really going to be using is Avogadro's number that comes from the definition of an AMU. We're going to use this to talk about the numbers of particles and the number of moles. One very, very common example that's very similar to this is to use a dozen when you're talking about the number of eggs that you have. So say you want to buy 36 eggs. Typically, you don't go to the store and think about, I'm buying 36 eggs. You think, I'm going to buy 3 dozen eggs, because eggs come in dozens, 12 eggs per dozen, so 36 eggs is 3 dozen. So you usually think of eggs in terms of how many dozen you're going to buy. Maybe not, you don't think of it that way when you're thinking about cooking something, but when you buy them, you think about them in terms of dozen. And we'll think about often the number of atoms or particles in our ideal gas in terms of how many moles of those particles do we have. Okay, let's move on. The number of moles of a material, the number of moles of atoms in an ideal gas, is usually written with a lowercase n, or else at least I'll write it with a lowercase n. And that's equal to the number of particles. So let's distinguish between these two n's. A lowercase n means the number of moles, okay? While a capital N, this means the number of particles. In other words, the number of atoms, say, for example, in an ideal gas. We take the number of particles and we divide by Avogadro's number, and that tells us the number of moles. So very much like if we have 36 eggs, we divide by the number of eggs in a dozen, and that gives us 3, which would be the number of dozen eggs. So very, very much like that. So let's do an example here. Let's imagine we've got a gas with 5.00 times 10 to the 25 particles, or atoms. The number of moles will then be the number of particles divided by Avogadro's number. So 5 times 10 to the 26th times 10 to the 25th divided by 6.022 times 10 to the 23rd, Avogadro's number, gives us 83.0 moles. So we will use both of these numbers in different ways, well, in a similar way, but in different equations. So sometimes we'll talk about the number of moles, sometimes we'll talk about the number of particles in the ideal gas. Just to give you an idea of how big this number is, Avogadro's number, if you had a mole of, let's say, tennis balls, so a tennis ball, something like that, if you had a mole of them, they would cover the entire surface of the Earth to a depth of 250 kilometers. So if you just think about that, that is a huge, huge number. So when we're talking about a mole of atoms, we're talking about a very, very large number. And that, although you might think, well, that's going to be impossible to deal with, actually in some ways it makes it easier to deal with. Because there are so many, averages tend to be much more easy to calculate. We can assume that the material has a particular average values. We don't have to look at any particular atom. We can just use average values. Okay, so let's go back to our ideal gas and see what kind of properties can we say the ideal gas has. Actually, sorry, I wanted to take a quick look at the periodic table before we move on to the ideal gas. I want to talk just a little bit more about the AMU. So here's a periodic table of all the elements, and let's take a look at one in particular. Let's look at carbon here. So let's focus on carbon. So the letter C here stands for carbon, and I want to take a look at these numbers and see if we can understand what they mean. First of all, the 6 up here, this is the atomic number. And this tells us how many protons are in the nucleus of carbon. So whatever these numbers are, it tells you the number of protons in the nucleus. Carbon has 6, boron has 5, nitrogen has 7, etc., etc. And then down here, what is this number here? It's the atomic mass of the element, the atomic mass of carbon. Now, well, why is it 12.011? Why isn't it just 12? We used the atomic mass, we used carbon to define the atomic mass unit. Why isn't the mass of carbon exactly 12? Why is it 12.011? Well, we can think of this number in 2 different ways. First of all, it's the average, it's the mass, sorry, let me back up. It's the average mass for an atom of carbon, a naturally occurring atom of carbon. Well, there are different isotopes of carbon. There's carbon-12, like I said, the most common, but there are other isotopes, carbon-14 and some others. And the presence of those other isotopes makes the average mass, carbon-14 will have a larger mass than carbon-12, it makes the average mass per atom a little bit larger. So the average mass per atom is 12.011 AMU, atomic mass units. We can also use that number as the mass in grams of a mole of carbon. So 1 mole of carbon, and let me emphasize, a naturally occurring sample of carbon, which will mean it's a mixture of different isotopes, that will have a mass of 12.011 grams. So this number, the average mass of one atom in AMU, or the mass of a mole of naturally occurring sample of that element in grams. Okay? Very good. Now let's move on to the ideal gas.